Okay, welcome back, and this is part 2 of week 6, and this section we will talk about radiant floor heating. So, radiant floor heating is very optimal for so many reasons, and it's very suitable for when you have big surface area. And why is that? I would like to explain to you how does it function and why is it different than other heating appliances. So, for example, if we look at the baseboard radiator here, the main mode of heat transfer is natural convection. And convection, as we know, is using fluids like water or air to conduct heat and to take heat from one place to another. So looking at that here, this is convection. Even though we call it a radiator, it's mainly doing convection. The radiant floor heating is the only, actually, maybe not the only, but one of the most common ways, most dominant way of doing radiant for radiation for heat distribution. So looking at let's say this is the floor of a house, and this is the area of the floor, and this where we are heating the floor to heat the room. Okay, if you look at the equation for radiation, this is our original equation where we use Q equal A times U times delta T. In this equation we use Q equal, it's a little bit different. This here is epsilon. This is the it's called the Boltzmann constant. Actually, this is the Boltzmann constant, which is just a constant for radiation from waves to heat. And this here is the opacity factor for color from 0 to 10 for bright colors to dark colors. So dark color absorb more heat, and bright color give off more heat, and this is dark color. So dark is here and bright is here, and this is the opacity factor, and this is the Boltzmann constant. It's the constant between a relationship between waves and okay, now it's better. So you can see the factor over here, and then you go with the temperature difference this time, and it's raised to the power of 4, and we have the area. So these two things we have no control over, and the temperature is the most important, second most important factor, and then the surface area. So if you look at the temperature of the radiant floor heating, it could be sometimes 85 degrees Fahrenheit, but we rely solely on the surface area. So the bigger the area, the bigger the projection we'll have, and there's also something called the view factor. I don't want to go too much into the science of it because that's kind of like beyond our scope, but this is T hot to T cold raised to the power of 4, and the area. What you need to take from this kind of confusing equation is the surface area is very important, and the view factor, how much of this surface area is facing the space that you would like to heat. Okay, enough of that. So if you look at your book, what you need to look at in the last page is your equation here, which gives you the radiation rate. So if you want to calculate selection, if you go to radiator selection, you can see this is for the steam, this is for water, and this is the equation we just used last video. And this is here our equation given for radiation. So this is R is the radiation rate, and area is the area available to radiate heat, whether it's floor or wall, and temperature difference between the water and the room. Okay, so let's move on to this. It's very comfortable temperature profile, and we did talk about the temperature profile, and we said that it's better to have the floor to be warmer than the eye level. And if you go to the book, that's in chapter 6 and page 86, you'll see some tips and some of the examples we worked out here in class. So it has the best temperature profile of any other heating system. Let me try to make a small drawing here. So this is the floor, and we have the water running through tubes. Why the tubes are like this, I have no idea, but just bear with me here. This is 85 degrees Fahrenheit. This will be 85. and it will radiate heat. So if there's somebody here, yes, it is, and the temperature will be here at 65. So the feet and the temperature will decrease as we go up, and this is the most comfortable temperature level for uh, living space, to have the floor to be hot where your feet is, your body is hot, and your face to be a little bit cooler. That's kind of more comfortable than having hot air blowing through. You have frost air, you have the hot air coming at you at 85 or 90 or whatever. So that's the most comfortable part. And going forward, it's a perfect match for each heating zone. You can change the temperature of the water for each heating zone, and you can zone using loops. Every room will have its own loop. So, and there's a schematic in the book that shows that. Lower operating temperature, usually between 85 and 95, and that is very perfect because you can utilize heat pumps or appliances that produce less heat than gas or oil. So it's a very good match for so many low heat appliances. The air in the room is stratified, and all the air is the same temperature, and no region is hot or cold. What does that mean? So we have more uniform temperature throughout the room, which is better than having, if you have a room with the basement radiator here and the basement radiator here, probably this area here will be hotter than the other area. So this will be probably 120, or this will be, if you bring it closer to it, and the heat will disperse to the entire room. So it takes time for the room to be the same temperature. If you take spot of temperature in here, they will be completely, every spot will be different. Meanwhile, if you have a heat earlier for heating, it will kind of give you a uniform temperature throughout the room. Okay, moving on. There is no visible heating unit, so you cannot hear it, you cannot see it. It's just the floor or the wall. It's very quiet, no noise coming from the system. It does not stir up the air, and it does not need cleaning, and you can flush the water once in a while. Very versatile. Can be used with solar, heating panels, geothermal, or low operating temperature. Again, we say, think about it. Hot water, the steam uses 210, above 210 for boiling temperature to make steam, and hot water uses 180 degrees. And if you were to use regular heating, you need water to be at 85 or 95 degrees. But it is, again, very slow acting. Okay, the limitations, again, it's very slow acting. It takes a while to heat the place, and it's the kind of system that you leave on all the time, because it's not going to heat very quickly. It will take a few hours for the temperature of the room to reach the desired temperature. Of course, each blocking is a problem, and we talk about that when we compare systems. If you have carpet, if you have big tables, probably the projection of the heat from the floor to the room is going to be kind of held back. There's no filtration in of the air. I mean, if you want to compare that with forced air, and leaks in the system are very, as rare as they are, they can happen, but they can be very damaging. At that time, it will cost too much to fix those parts, especially if they are embedded into the floor. Building material has to be able to tolerate the temperature and the fluctuation, especially if you're going to put these parts into like dual ceramics, or you're going to pour some cement on. System specification. Okay, that kind of covers what heat radiated for heating, and there are a couple of examples in the book. So this is some of the specification about radiated for heating. Use a manifold, and you think about these kind of circuits, kind of like electrical panel. You have your panel, you distribute the power to the entire room. Same thing that will happen here with hot water and cold water. So each room will have its own loop coming from the manifold to heat the room and coming back to the cold manifold. And that's going to help out in zoning. Tube size, tube length, and tube spacing. These are all, when we look at it again, these are all contribute into what's called the radiation rate. So this is the radiation rate, and I'll use this example here. If I have a room, so the tube size, so I'm going to have tube going all the way around the room. tube size, how big is it, big or small, and the length, you might need to have longer loop inside the house, and the spacing between them. That's what I mean by the spacing. Filling, are you going to need it to fill with air? Are you going to put some kind of conductive material? Sometimes you put gravel on them to help the conduction, because you want the floor to be completely warm. And radiant floor heating can also be used to heat walkways or stairs as well. So these are, make this bigger so you can see it. This is the tube size in here. This is the spacing between them, and the filling, what you're going to fill that space with. And once the system is done, it has to be pressure tested, it has to be blocked and pressure tested, because once it's sealed, you don't want to reopen that again. The inspection has to be coordinated with other construction contractors, because again, you're going to be embedding water towards the side of the floor. Okay, calculation, this is the equation that I provided before, which is radiation rate times area times delta T. The radiation rate is given and provided by the manufacturer, and they will give you also the spacings and the specification for this installation. It's giving, the radiation rate is given as BTU hour per square foot, based on the spacing and the tube size that has been provided. The area is whatever area is exposed for the hot surface, whether the entire floor or the wall in square foot. It's an example. So a room that has a heat loss of 4,000 BTU hour. Let's write that. So 4,000, and then keep the equation here, Q equal radiation rate times area times delta T. 4,000 BTU hour. T is 75 for the room. Radiation rate is 10. And the room is 8 by 10. That's a very small room. Just for an example of this. Maybe, I don't think it's even that. 80 foot square. And what is the water temperature required for that room? So, you know that delta T is temperature of the room minus temperature of the water, or the other way around. If you get a minus degree, it should be the temperature of the water minus temperature of the room. If you look here, I'm going to show you. I kind of manipulated the equation for you. It's the same equation over here for the radiation rate. If you would like to find the dT, this is the progression of the equation. If you want to find the temperature of water required based on the heating load, this is how you do it. So temperature of water, you can use this equation over here, which is Q over RR times A plus the temperature of the room. So I'm going to use this equation here that we already have, which is T water equal Q over RR times A plus T room. So I got that. I'm going to do this here. So we had 4,000 degrees, and here's the radiation rate, which is 10. 10 times area is 80, plus, make sure you use the parentheses, temperature of the water, the room is 75, and I think I have the answer over here. So that's how it's done. And I found out the temperature of the water required is 80 degrees. You can control the temperature of the water based on the manifold, or you can use some kind of mixer valve as well. Okay, another example here. And this time we are looking for the panel area. So this example, we have a temperature as 20 degrees, radiation rate is 5, heat load is 2000, and this direct substitution, and you can find the equation here in page 159. Okay, this is the area required, is 20 foot square for the you need at least to get that kind of use this panel, this rate, you need 20 foot square. It's good to have reference of this equipment, how it's done, in case one day you come across waiting for heating and you could ask questions and you want to use a kind of simple bucket to handle the calculation. Okay, I will pause now and I will go through codes in the next video.